the homework. In general, I thought it was okay, but there are a few issues that I just wanted to bring up, and also a clarification. 2 clarifications that I had. All right, so homework 2. So the biggest issue that I saw was death by Avogadro. There were a number of people who forgot to get rid of Avogadro's, the moles, out of their equations. So remember that in 1.4 and 1.5, we said that the average energy that we put our gas at is RT. Right? And the idea was to equal E, the average energy of our system, to the particle in the box energy, and solve for N. Right? What's the energy level associated roughly with this average energy? And if I just put RT in here, we have RT equals h squared n squared over 8 ml squared. I'm going to do the unit analysis here. On the left side, R has units of joules per mole per Kelvin. And of course, temperature has Kelvin, it's in Kelvin, not T. Units of Kelvin. So the net units on the left-hand side of this equation are joules per mole. And I won't go through the analysis here on the right-hand side, but we know what this comes out to. It comes out to energy. This is the energy of the harmonic oscillator. And the units on this side come out to joules. Okay, so times n squared. N is unitless because it's just an index. All right, so in the end, you're solving an equation where you have joules per mole on one side and joules on the other side with a unitless number, and so you have to get rid of moles on this side, right? So most people were off, and ended up being off by a square root of Avogadro's number. So people's n's, for instance, were like 10 to the 13 when they should be 1, or around 1. That's because they forgot this square root of a mole to cancel out. Okay, so remember, just kind of a really, really good kind of. Now I put this in there partially to be helpful, to especially the students who didn't take CHEM with us last semester, who haven't seen Boltzmann's constant, which is Avogadro's number divided by, right, it's the per molecule gas constant. I'll write it down in just a second. So I put in R, but just got to make sure that you get your units right. But moles, in general in this class, moles are your worst enemy. All right, we're going to do most everything we do in this class is one particle. You're always going to want to get rid of moles. And I think most people figured this out, but I did get some emails during the week. But of course, this also matters for mass as well. Some people were writing for helium M to be 4 AMU, which is grams per mole, which of course is off by a factor of 10 to the 26 or something like that. Okay, so again, you could do everything in moles. So if you converted your mass to kilograms per mole, you'd actually get the right units here, and everything would work out. But again, you're still off by without doing that, you're off by a factor of square root of Avogadro's number, which is about 10 to the 13. Okay, so just remember that if I have something in that talks about things that are referenced to moles per mole, kilojoules per mole, Avogadro's number, things like that, generally a good option is to get rid of moles. Okay, I often write things in per mole units because, again, it's easier sometimes to write things in per mole. But for calculation purposes, we'll want to make sure to get rid of it. That was the big problem that I saw. A couple people had some integration problems, but we can deal with those on an individual basis. But most people seem to have gotten the point. I want to mention the last 2 problems, 2.6, because I think that was the one that most people kind of had struggles with. And perhaps I wasn't as clear with what I wanted you to calculate in 2.6, but that's okay. So let's kind of look at it. So 2.6 asks you to calculate something called the density of states. DOS, I'll call it. The density of states, which is this density rho. It's a function of energy. And I said it's equal to the derivative of the quantum number n with respect to E. evaluated, it's the slope of that curve evaluated at the average energy of our system. So what is this physically? This is basically saying how much does N change, right? How much does the energy level change? Remember, N just tells us what the energy level is upon changing energy by plus or minus 1 unit. Okay? And so what this says is that if you move from, say, minus half a if you're at some point, some energy point, and you ask, how does N change if I move half a joule lower in energy, or how much does N change when I increase by a joule? How many energy levels are there? Right, what's the density of the possible energies a system can have? But one of the things that I identified, and I posted this on Canvas as an announcement, and some of you saw this immediately, is that this is very large for us. 1 joule is huge. Right, because if you saw it in 1.6, sorry, this is all 1, not 2, sorry, 1.6. 1.6 RT, you probably calculated is about 10 to the minus 21 joules at 300 Kelvin. All right, so a molecule, an atom, a helium atom at 300 Kelvin on average only has 10 to the minus 21 joules. So thinking about how much the energy changes when you change it by 1 joule is ridiculous, because you're never going to have that much energy. It's not a realistic kind of, it's like measuring how many total states there are, but we're only looking in the region that the molecule can exist, right? So if I add a joule to a molecule at 10 to the minus 21 joules, it's in a very, very different world than it was originally. Right? So what I'm interested in is rather how much does N change when we move by this small unit. So what we really wanted to calculate, and this was my announcement, is that the energy, the density of states at the energy is RT times this derivative. Right? And this is the number of states per unit RT energy. Right? So this kind of tells you roughly locally in the kind of range of energies that a helium atom at this condition would have, how many states are available, how many possible energies can it have. And what we saw the results was that for 1.4, which is 10 to the minus 6 Kelvin, and length is 1 micron, right, a microscopic cold box, rho is about 2. Okay, so if I move my energy probe a little bit around the energies that most of the molecules are, which is at RT, if I move it around, I only change N by roughly 2. Right, which means there's only a very, very small number of energy states to pick from. Now in a particle in a box, the energy is proportional to the momentum squared because it's kinetic energy. Therefore, it's proportional to velocity, or the speed. So what this says is that there's really only roughly plus or minus a few states or different velocities that the atoms in this box can show, right, that they can be at. Very, very small number. Right? And my interpretation of this is wave-like. Is that the way that you represent the particle is by representing the sum of all these particles. They're all moving at different velocities, but they're only moving at roughly plus or minus about 4 velocities, 4 or 5. Because this is a distribution, so if you have a mean number, it's plus or minus this number. There's about five possible velocities that the vast majority of the molecules in this gas exist at. So they're all moving together at the same rates and the same speeds, roughly. And this is very wave-like, right? The gas can be represented kind of as a wave of a single frequency, or a very small set of frequencies, or a small set of energies. Right? So this is very quantum mechanical-like, right? That the only possible energies are very, 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 very small number, and they're widely spaced relative to RT. And so you don't change the energy that much of the system by moving across your possible energy distribution. And then in 1.5, I'm just going to write it here, which was 300 Kelvin in 1 meter box, rho is 3 times 10 to the 10. All right, so what does that mean? It means that in a macroscopic box, if I move my energy probe through the range of the most probable energy values for my gas, there's roughly 30 billion states to choose from. 30 billion different speeds, 30 billion different momenta, 30 billion different energies, however you want to think about it. So in my small box, I move my energy around my energy scale of my system, and I only have plus or minus 2 states to choose from. Right? There's a total maybe 5, because it's at the average state plus or minus 2. But in 1.5, you have 30 billion states to choose from in that same energy range. So what does that mean? It means that when you look at your atoms in a macroscopic box, they're in a very, very wide range of velocities, energies, momenta, whatever you want to think about, very broadly distributed. There's lots of states to choose from, and the spacing between the energy levels is very, very small, right? There's 30 billion possible states in RT than there is, and in the small box there's only 2, right? So you can think about the limit. What does the energy level structure for the box in 1.4 look like? Well, in 1.4 you calculate that the average level it's in is 4. So it's basically at the ground level. That means there's the 3, the 2, the 1, the 5, and the 6. 1, 2, 3. Oh, sorry, I missed one. Right here. 3, 4, 5, and 6. And the density is plus or minus 2. So it means there's only about 2 states in the region. So that means that roughly all of the molecules are just in these states right here. 2, 3, 4, 5, and maybe 6. Right, so most of the molecules exist in these couple of small states, and then there's this whole energy region in the middle. Let me get a brighter marker, where there are no energies. Right, the system doesn't exist in any energy at once. The gas doesn't exist at any energy at once. It can only exist at 4 different energies, or 5. Right, it can only exist between these 3. Right, so if you have a mole of helium atoms in this tiny cold box, a micron, the particles act like a wave. They're very wave-like. They're all condensed into a small number of states, right, that have specific frequencies associated with them, or energies, however you want to think about it. But in the case of a 300 Kelvin box, and L is 1 meter, N here we calculate in 1.5 to be about 7.1 times 10 to the 10. Right, so the average energy level is the 71 billionth. And I said that the density of states, which is how many states are nearby within the unit of RT, is 3.0 times 10 to the 10. So there's 30 billion states to choose from in this range, this energy range. Right? So what does the state level, the level structure look like? Well, this is completely underestimating its density. Right, but you have 30 billion states in the same region here to choose from. Right, so if you have a mole of gas here, right, and assume that all of the states are roughly equally, there's an equal number of molecules in each of the states, which actually is not true, but let's assume that. Right, you have roughly a micromole per of these states, right, which is about 10 to the 18 molecules per state here. Right, because there's only 6 states that they typically are in, right? So about micromole. But here you have 30 billion states in the same region. If we have a mole of atoms in these states, then on average there's only about 10 to the 12, 10 to the 13 molecules. There's 1 million to 100 million or a billion times less molecules per state on average in this gas than there is here. So this gas is very dispersed. The energy spectrum is very broad. And the spacings between the energy levels are basically you can't distinguish them. It's just basically a block of lines, of states. Right, so this kind of looks like a continuous energy distribution. Right, you can have any energy you want. And this is discrete, or quantized, however you want to call it. Right, there's only a couple to choose from. Right, this idea of having continuous energy, that the system can be at any energy around the average. Well, this is just an ideal gas. This is classical. Whereas this says that the particles can only be at a very, very small number of energies, and they're distinct from each other. They're not all blurred together into a big band. They're distinct energies. So this is very quantum mechanical. And the point that I was trying to get across from here is that we've gone from a wave system, a wave-like gas, a quantum mechanical gas, which is where everything has these, all the properties of a quantum mechanical prop with the waves and the not everything is equally distributed in the box, to a system where everything is equally distributed in the box and is all randomized. And that's ideal gas. And the point of the matter is that what I'm trying to get at here is that that quantum mechanics in classical physics, thermodynamics, ideal gas, chemistry, whatever you want to call it, they're not two different theories. It's the exact same theory. Except what's happening is that we've chosen the experiment we've done. One we've done in a microscopic region. It's the microscopic box. You can see microscopic physics. Here we pick a macroscopic box. You see macroscopic physics. So the conditions of your instrument, or the conditions of your experiment, determine the limit that you look at things. Right? So it's a function of the temperature, the energy, the size of the box. It's not a function of the physics. The physics are the same everywhere. Everything's still quantum mechanics. It's just a matter of, is the system that you localize your molecules, your atoms in, quantum mechanical system, is it itself macroscopic? And if you put your system in a macroscopic box, then it acts macroscopically, right? Which is like an ideal gas in this case. Okay. So the idea is that ideal gases, they have high average occupation number. They're at high energy levels. They're way away from the ground state. The energy gap between the nth level and the n+1 level is much smaller than RT, which means that the gap between these levels is very small, right? This is where it's much less than RT. Here it is much greater than around RT. And this is equivalent to saying that the density of states at the energy is large. So a classical system, an ideal gas is just an ideal gas, really. It's nothing more than a set of particles in a box, but you've made the box in such a way that all the gaps between the levels, right, the energy spacings are much, much smaller than the energy scale of your system. Right? The energy scale of our system is this, RT, 300 Kelvin. All right, and it says that the spacings between all the energy levels in that energy region are much, much smaller than the gap, or about the amount of energy we have. We have this much energy to pick from. That's our distribution of energy on average. We have 30 billion states to choose from versus only having 4. Okay. So this is what an ideal gas is. And in fact, if you take this, all these numbers and that density of states, the calculation that you do and all of that, and take it to 3 dimensions, and then take it for n to go to infinity. So you go basically to atomic or gas-like system where you have many, many atoms. You get Pivner back, right? You're one step away from Pivner at this point. Right? You just have to put everything together and average it thermodynamically, and you get Pivner out of this. Right? Because if you remember, Pivner has a volume in it. Here we don't have a volume; we just have a length, right? So once we have 3 lengths in 3 directions, we have a volume, and you can just go from there to Pivner. It's not too hard. I'm pretty sure if you have the textbook does it from this assumption. All right, so that was homework 2. People had pretty good explanations for this, but I figured I'd clarify it to everybody. Okay. Any questions about that? Okay. So let's continue. I'd like to first. I did not have my... Oh, I did. Okay, great. All right, good. I would like to continue with our exploration of molecular vibrations, and we're kind of at the place now where we can start really talking about molecules. Okay? But we need to... I kind of closed the class last time with some concerns about our harmonic oscillator. All right, so I've redrawn my harmonic oscillator. We have what we're going to do for all today, we're going to look at diatomic molecules, all right? But we've been doing that the whole time, but just to remind you, atoms A and B, they have masses Ma and Mb, and we can define a harmonic potential oscillator based on the strength of the bond, right? K, that's the strength. I'm going to define a new notation here because it'll be useful today. Is I define the equilibrium bond length of the bond as R sub E. Right? This is standard chemical notation. But I've been using these X's and X naught and stuff like that. I'm going to change that from now on. And we're just going to use R sub E for the equilibrium bond length. Okay, so anytime you see that R sub E, that means that's the bond length that makes the minimum, the potential minimum. Right? That's the equilibrium position of the bond. All right, I'm just changing my notation a little bit. Keep things consistent. And of course, because it's a chemical bond length, it's obviously got to be greater than 0. Right? An example is that for CH bond, RE is kind of around carbon-carbon bond. For carbon-carbon bond, the equilibrium bond length is around 1.5 angstroms. Okay, so it's a strictly positive number. All right, so let's think about our magic molecule AB at some bond length that's sitting right here at the bottom of the potential. And we want to stretch it or compress it. All right, so let's do it in, let's assume that the potential that I wrote here, the harmonic potential, this parabola, is the real potential for the bond. Right? This should be a reasonable thing to assume. Now let's think about what happens as the bond gets compressed, stretched or compressed along this potential. Well, it doesn't matter which way I go, the energy response is exactly the same, right? It's symmetric about R sub E. So the force that's required to stretch or compress a bond by some distance from R sub E is the same regardless of which way I go. Okay. So let's just check both examples. Let's go to the left, right? So R sub E is going to we're going to compress the bond. R sub E gets smaller and smaller. Right? R sub E is some positive number. Eventually we're going to hit 0. R equals 0, right? We're going to compress it so much that the bond length is now 0. Okay, what does it mean for the bond length to be 0? Well, that means that the two atoms are directly on top of each other. They're overlapping. Right? Typically, the way that we define these bond lengths are from the centers of the atoms. Okay? So R equals 0 means that the atom centers are right on top of each other. Well, that's a problem because what's at the center of all our atoms? Well, a nucleus. Right? A nucleus is positively charged. So what this is saying is, when I put my system here, I'm now in a position where the two nuclei are directly on top of each other. They're overlapping. They're positively charged. They should repel each other. Should repel each other very, very strongly. All right, but let's think about going to the opposite side of the potential with the same distance from R sub E. All right, so let's stretch it to the same energy on the other side. And ask the same question, what's going on here? Well, if R sub E is 1.5 angstroms, for instance, this is 1.5, then this is 3 angstroms. Okay, so what have I done chemically here? Well, I've stretched the bond to twice its length. All right, so let's just think now, all right? So I have two equivalent energy points in my harmonic oscillator potential. One where the bonds are 3 angstroms apart, the atoms are far apart. And one where the atoms are directly on top of each other. What the harmonic oscillator says is that these have the same energy. But that should be a problem, right? Because they clearly do not. Because what happens when the atoms are at 0 together? Well, you have very, very strong repulsion, certainly between the nuclei, but also between the electron clouds of the atoms. You know that atoms are attracted. We'll talk more about this, but atoms are, we talked about last semester too, that all molecular matter is attractive to itself. But if you get things too close, they repel. Right? So we have this repulsion at low distance, short distances. Right? We have this repulsion between, say, electrons, or nuclei, whatever, at short distance. And then what do we have at the opposite end of the potential, the long distance? Well, the only thing we've done there is just stretch the bond. Right? We've pulled the atoms further and further apart from each other. Well, they're not going to repel each other at longer distances because the repulsion is a short length event. It goes as 1 over r and 1 over r squared. And so there's not repulsion. If there was repulsion at 3 angstroms, then there certainly would be repulsion at 1.5 angstroms. But there's not. That's a stable bond. So that must mean that this bond would have to be weaker at 3 angstroms than it is at 1.5. I've got to break that bond a little bit. But what have we done when we broke our bonds? Well, we've made them less attracted to themselves, the atoms. But we haven't increased the repulsion at all. There's nothing to repel. We've only pulled the things further apart. They repel when they get close, not when they get further. So on the left-hand side, we have severe repulsion that we predict chemically. And then on the other side, we have no drama at all. It's completely free. It's just the bonds just kind of falling apart. All right, so what that should tell you right now is that this probably doesn't work, right? That this is not capturing the physics that we expect for molecules. So let me write that down and kind of formalize that. Let's do the short range one, right? So at small r, as r goes to 0, no drama from electron nuclear repulsion. All right, so I'm going to call this problems with the harmonic oscillator. So repulsion doesn't seem to play a role. We're not considering it at all. And then let's think about this is as r goes to 0, not a as r goes to 0. As r goes to 0. That's an arrow. Sorry. So there's no drama. But let's think about what happens as we stretch this bond even further than 3 angstroms. All right, let's take it to 10 or 20 or 30 angstroms, right? What happens to the energy of the molecule as we keep doing that? Well, it just keeps going up and up and up and up, right? The potential is a parabola, so it never flattens out or goes negative or anything like that. It just keeps growing forever. So what that says is that as we start to pull our atoms further and further apart from each other, they will try to compress back together harder and harder and harder. Right? But if you take 2 atoms and pull them apart hard enough, the bond breaks. Right? The bond breaks. So of course, if you try to rip a piece of paper, as you rip it, it doesn't try to unrip itself harder, it just rips. There's eventually some force that you apply, strong enough force you apply to these bonds that it breaks them. But this never breaks. All this says is that the bond, the force of the bond, the force of the spring gets infinitely more and more strong as the bond gets stretched and stretched and stretched. It never breaks. Right? So this bond never breaks. Right? Bond is always connected, right? Of course, if you have 2 atoms at infinity, I put an atom one end of the Milky Way and an atom at the other end of the Milky Way and calculate their interaction, right, the strength of their bond, it's 0. Right? They're really, really far away. Effectively, it's 0. Right? But what does this predict? If they were at infinity, the spring has an insane amount of force, right? It wants to pull these 2 atoms from super long distance, this 100 light year bond length, that wants to come in together at some insane force. Obviously, that's not what happens. So at small r, the system acts as if nothing happens. There's no repulsion, there's no electrons, nothing, just totally normal. And also, when you stretch it to really long distances, the bond never breaks. It's always bound. Right? So these are obvious problems. Right? These are things that we need from chemistry. That atoms repel each other when they're close, and that the bonds break when we pull them far apart. And the harmonic oscillator doesn't give us either of those options. Right? Again, think about this as somewhat like a curved particle in a box. The walls go up to infinity. They just keep growing and growing and growing. Right? So there's going to be more and more energy levels associated with this bond at higher and higher energies. But eventually the bond should break. But this predicts that it never does. Okay, so we have to fix that. And then we have to ask the next question, which is, if this doesn't give us chemical properties, why do we even consider the harmonic oscillator to begin with if it doesn't even predict basic qualitative chemistry? Right? So I want to explore that today. First, I want to suggest what we should do is come up with a new potential for our bond that looks more chemical. One that includes the repulsion at close distances, and one that accounts for the fact that the bond will break at long distances. And then what we'll see is that the harmonic oscillator does work, but it only works at a very, very specific region of your potential. And that is very, very close to equilibrium. So what the harmonic oscillator really is an approximation for the lowest lying vibrations of the molecule. And it actually gets worse as we go to higher and higher energy. We'll see that. I have examples for this. And we'll see how we can correct for it. Okay, so let's brainstorm a new potential. So what do we want? Well, we want repulsion, right? Which means that the potential as a function of R should go to infinity as R goes to 0. All right, the atoms will never perfectly overlap each other. So let's just make sure they never do that. Okay? So we'll basically say it's impossible for them to ever go to be overlapping. The closer they get together, the harder and harder it is for them to push together. All right, we'll do bond breaking. All right, we'll let V of R go to 0 as R goes to infinity. Okay? And the idea is that the potential will tell you how repulsive or how attractive the interaction between the two atoms are, the potential energy. And so if there's no attraction, there's no repulsion, meaning no bond, then the potential is 0. Right? So it's going to go to 0. And then we also need to recover the equilibrium stuff, right? That we need a minimum at R equals R sub E. So that means that the derivative of the potential evaluated at the equilibrium position is equal to 0. Okay, it's nice and flat. It's a minimum. So this is a minimum. Oh, sorry, let me spell that properly. Minimum. There we go. Okay, so those are our 3 kind of behaviors. There's a couple of other things we need to consider, but I think these are ultimately kind of summarize the most important characteristics of what a molecular potential should look like, what a bond should look like in terms of energy. Right? It goes to infinity when the atoms overlap. It goes to 0 when the atoms are infinitely apart. And there's a minimum where there should be a minimum. Okay, so let's draw that figure. And again, there's lots of different ways to represent this, but I'll come up with a really nice formula for us to use. We'll plot bond length versus potential. And we know that, so let's start at long distance. We know it goes to 0 as it goes to R equals infinity. And then we know that it goes to infinity at small r, right? So it has kind of a vertical line roughly there, and it's flat at R0, and the only way to get a minimum here is for this to go negative to reach a minimum, and then slowly asymptotically converge to the line, like this, something like that. Okay, so we have V goes to infinity here on the short range part. We have V goes to 0 on the long range part, which is bond breaking. And then we have at R sub E, our equilibrium bond length, the minimum of our potential here. Okay. We can derive a few things, we can make a few statements about this, and we will. But this kind of gives us the picture that we want, right? That it goes to infinity at the short lengths, right? The shortest possible bond length can't be 0. Basically, it's impossible to do that. Or we're going to assume it is. and at distance it goes to 0, right? So there's going to be a minimum in between, right? And this is our bond potential, right? This is the region, this part right here, this is the region of distances where the two atoms are attracted to each other and they can form a stable bond. Right. So we use a specific potential, named potential, very famous one, to represent this. And I think I introduced it last class and last semester, but I'll do it again. We'll see it time and time again. This is what's called the Morse potential. Right, and it has the reason why we use this Morse potential, there's a lot of reasons, but and again, it's just an approximation. This is not a real model for a bond, it's an approximative model. Right, it turns out that real bonds, diatomic bonds, they have a slightly different form, a little more complex, but in general, this gets the right answers, and we'll see that. It's pretty good. And the function for this is V of R, and there's some constants which I will introduce to you in just a second. The first constant is this d sub e. It's a number, and it's 1 minus e to the minus beta r minus re, and this whole thing is squared. Like this. Very, very simple formula. All right, so as you can see, there's a few constants in here that we have to define. This beta, this d sub e, and I think that's it, right? This is an e, we have an r, right? This is just your parameter. R sub e is the minimum on your length scale. And what is d sub e and beta? Well, d sub e is what's called the dissociation energy. All right, and it's really easy to calculate from your plot. It's the distance in energy between the minimum of your potential in energy to the dissociation limit, d equals 0. Okay? So again, the idea is that you have a bond, okay? And it's at the equilibrium position, you want to break it. Right? How much energy do you need to put into that bond to break it? Well, you need to put in the right amount of enough energy to take it so that the atoms go to infinity. Right? So we have to go from here to here. So how much energy do we have to put on in? Well, the difference from here to here, which is d sub e, the dissociation energy. Okay? So this is basically the bond strength, if you will. This is how much energy it takes to break the bond along this coordinate. It's kind of like a bond strength. I wouldn't call it a bond strength because bond strength is defined differently. Like if you go into Google and type in the bond strength of carbon and hydrogen, that number actually comes from a collection of these dissociation energies because there's different ways to break a carbon-hydrogen bond. All right, but they're similar in size, but it's not exactly the same number. All right, so you can kind of think of this as the bond strength. And then we have this beta term. And there's different names for this beta term, but I like to call it the anharmonicity term. And it's proportional to the stiffness of the bond. Is it 1 over the stiffness? No, it's the stiffness. So when beta is large, so I'll just write this, the width of the potential across two different points that have the same energy. This width here is, let me see, it's proportional. So if beta is small, yeah, is proportional to beta. All right, so beta kind of tells you kind of how floppy this bond is, right? How rapidly does the energy increase as you move the bond a little bit? All right, so B kind of tells you something about the steepness of the potential. All right, so let me get rid of that alpha there. That's not an alpha; it's proportional, approximately beta. It's a little off from beta, but it's close. So the idea is that if you have a really, really floppy bond, and you got your diatomic molecule's got a slinky for a bond, it doesn't take a lot of energy the energy doesn't move a lot when you stretch or close the bond, right? It moves very shallowly. But if you have a really tight bond, then moving it a little bit increases the energy a lot. So beta tells you how much does the energy increase as a function of the displacement. Okay, so small b, I'll just write that. Small b is floppy. Actually, I'll write it like this. Small b and dE is a weak floppy bond. And large is a strong, stiff bond. Okay. And the units of these, let me just write the units down. D sub E is an energy, so it's in joules, or equivalent. We'll do things in other energy units, but joules are fine. And beta has units that are inverse length. Inverse length. Okay. So this Morse potential is actually really, really useful. As I said again, it is not a perfectly accurate model for a diatomic bond. It is an approximation for one. It is taking our harmonic oscillator toy and making it slightly more accurate. I'll show you that, in fact, it gets us really close to the right answer, much better than a harmonic oscillator does. But it's not perfect, because in fact, the limit as r goes to 0 is not really truly infinity. There is some finite energy it costs to have the two atoms move across each other. But we're going to ignore that. And it turns out at long distances like out here, especially for some molecules, it doesn't just go immediately to 0, but it actually kind of continues to increase. Because there actually are these magical long range effects that atoms can have at really, really, really long distances that we're ignoring here. Right? So there's some long range effects we're ignoring for attraction, and we're overcompensating for the short range effects. But this will get us really close to the right answer. All right, now the question is what does this have to do with the harmonic oscillator? Right? Why am I presenting this and not just using the harmonic oscillator for these predictions? Well, let me explain it to you graphically, and then I'll show you some data to prove that the harmonic oscillator is an approximation, but it's an okay one. So I'm going to go ahead and redraw my potential again. You don't need to if you don't want. I just want it for my use here. So let's say it looks like this. Let me make it look a little prettier than that. I'm sorry. I could do better. There we go. That looks a little better. Much better. Okay, so here's my Morse potential for some molecule. Right, and the idea for a harmonic oscillator, I talked about this briefly, is that the harmonic oscillator is the first approximation for what happens to a spring or a bond, what happens to its energy as we displace it. I showed that when you start from this point, the minimum of your potential, and you displace it, the first term in your energy that becomes dominant is the quadratic term, right? Because the linear term in energy approximating at this point as you displace is 0 because you're at a minimum. Right? You have dV dr is 0 here. Right, so the linear part of the potential is 0. Right, so the first non-zero part of the potential is the quadratic part of the potential. Right, so if I were to draw that, it would look something like this. Right, so this yellow line that I draw here. Right, this is right here is 1/2 d squared v dr squared evaluated at r equals re times r minus re squared. right? Which is the same as I said before, the same as 1F kx squared, right? This is the harmonic oscillator potential, R minus RE squared. Right, this is the harmonic oscillator approximation. Right, so if you think of the pink as being the real potential for the system, all right, this is what the molecule actually does experimentally as you stretch the bond. Our harmonic oscillator approximation is just our first prediction, if you will, an approximation for what the potential looks like at near the minimum. Right, so the harmonic oscillator is an approximation of the true V of R near RE. Okay, so when we're at bond lengths or energies very close to this minimum, the harmonic potential works really, really well. But as we start to increase the energy, right, if we shorten it, well, the energy starts to rise much faster than a quadratic equation will, or parabola will. Or if we go towards bond lengths breaking, then the quadratic potential increases faster than the actual potential. We start to get a disagreement. Right? So where does it agree best? Well, it agrees best near the bottom. Right? So for small displacements, right? So the harmonic oscillator is good for vibrations of small displacements. Say V equals 0, V equals 1, etc. Okay, right? So it makes a good approximation for things near the bottom of the potential, but the further we go up towards the dissociation limit, the worse it gets. All right? So remember, it's just the approximation. The idea is that we don't know what the potential looks like for the molecule, right? Imagine we don't know what it looks like. All we can do is we can take our molecule equilibrium and stretch it a little bit and see what happens. Right? We can build this yellow curve up ourselves by stretching the bond a little bit one at a time and seeing how it changes. And it's going to, but when we fit a parabola to that data, it's going to be an approximation for the function nearby, but the further we go away, higher energy we go, the less it will agree. Right? So we'll have to add additional terms. If we want to fit this function to some polynomial, right? We want to do a quadratic or something, we're going to have to add additional terms to fix it. Right? For instance, I could do this. I could add an additional term to my approximation, which is proportional to the third derivative of the potential. Right? This would be my cubic part. Right? And what would that do? Well, I'd get a little better agreement, but eventually it will start to disagree. And because it's a cubic, I can get an inflection point. And it'll start to disagree more. But if you think about it, if I've added this quadratic part, or this cubic part, this red part right here, I can get a little bit more of the potential determined because, again, with a cubic part, with a cubic term, I can get this inflection point, right? I can get a little bit of that curvature that the potential has here, and I can kind of start to get better agreements by adding a cubic term. Okay, but I can keep doing this over and over again, and that's fine. But this is why we have the Morse potential, right? Because if I just assume that instead of assuming a harmonic oscillator model making these corrections, I just assume that the bond looks like a Morse potential, then I can do quantum mechanics just on that approximation. And I end up getting really good results. So let's look at those results now. So let me show you. So the best way to prove this is by doing spectroscopy. So here I'm going to do some IR spectroscopy on HCl with 1 hydrogen 1 and 35 chlorine. Okay. And I'm going to look at a couple of different absorptions. Which we call transitions. All right, we're going to look at the 0 to 1 transition, right? This is going from the ground state to the first excited state. We're going to look at the 0 to 2 and the 0 to 3. All right, so this is exciting your molecule by 1 level of energy, by 2, and by 3. All right, and we're going to predict these lines using the quantum harmonic oscillator prediction. And we're going to predict it using the Morse potential. And we'll look at the experimental values to see what's right. Okay, so let's do the quantum harmonic oscillator approximation first. Quantum harmonic oscillator says that the energy of a level is h bar omega v plus 1/2. Okay, so the 0 to 1 transition is going to be the energy difference between the E0 and the E1 state, but these are all h bar, this is h bar omega in energy. This will be 2 h bar omega in energy because it's harmonic, and this will be 3 h bar, omega of energy. Of course, we have to calculate what omega is here. And I just looked it up on NIST. NIST has these numbers available. And for HCl, h bar omega is 2886 wave numbers. All right, we're using a different energy than joules here. We're using wave numbers. You guys are probably familiar with wave numbers by doing IR. All right, so we'll just stick with that, and we'll talk about wave numbers later. But anyway, it's an energy type. So the quantum harmonic oscillator therefore predicts. So that means that all of these energy levels are really easy to calculate for a harmonic oscillator. We just multiply it by 1, by 2, by 3. Right, so we know that the quantum harmonic oscillator approximation from 0 to 1 is at h bar omega. That's 2886. This one's going to be at 5772. And this one's going to be at 8658 wave numbers. Okay. So remember, 2886 wave numbers is kind of around where you find carbon-hydrogen stretches in your IR. You have the IRs here, they don't go high enough to do 57 or 86 at 100 wave numbers. So they're getting into the near infrared in your IR. So you need a different detector for those. But you can certainly measure them. Right? And now the question, of course, is what's the experiment? Let's look at the experimental numbers first before we do the Morse potential. All right, and not surprisingly, the experiment's right on for v equals 1. 2886. All right, so that's really nice, right? The harmonic oscillator gets the first transition exactly right. And by and large, for most molecules, and most systems, most stretches, most vibrations, this is true. The v equals 1, we'll look at this a little more carefully this week. So v equals 1 usually is very, very accurate. It's where you start to, right? That's for remember, that's the smallest possible displacement we can make, v equals 1. Right? But as we start to climb energy, we start to get into the region where it becomes less harmonic. Things are going to start to break down. All right, so let's go up to another factor of 2 of energy. Let's go to the next set. And the prediction for this is the experiment is 5688. As you can see, we're off by about 90 wave numbers now. All right, so we've gone from perfect agreement to a 90 wave number disagreement, which again is not bad. In fact, I'll calculate the error for this really quickly for you guys because I can't do it in my head. 688 divided by, minus 72 divided by 5772. All right, it's about a 1.5% error. So I'll write that really quickly. So this is 0% error, 1.5% error. Which isn't bad, but it's worse than before. All right, and so let's do the last one. This one's at 8347, right? The disagreement's gotten even larger. And that is 8357, 8658, 8658. This is a 4% error. All right, as you can see, as we go to higher and higher energy levels, we go from 1 to 2 to 3. Our disagreement basically increases linearly. It's actually more like quadratic, but it's a slow quadratic. From 0 to 2% to 4%, you imagine as I keep going, it gets worse and worse. All right, this is best case scenario. HCl, now I know most people, when you think of HCl, you think of ions, right? You find in water, of course, it dissociates readily. But in the gas phase, HCl, covalent HCl is just a normal molecule. It's got a strong bond. It's a very stiff bond, in fact, very stiff bond. HCl just have a very strong bond in the gas phase. So this is a very, very kind of stiff and strong bond. And so the anharmonicity, how much the actual potential deviates from the harmonic potential is relatively small. So this is kind of best case scenario, and you can already see that I'm already 3 energy levels deep, and I'm already about 5% error, right? So this is where this starts to deviate. All right, so let's look at what the Morse potential does, all right? So the Morse potential gets that correct, 0 to 1. And then now let's look at what it does here. Now I'm only off by 0.2 wave numbers. And then let me go up to the next one. My error is worse, but now I'm off by 5 wave numbers instead of hundreds. All right, so this is my point, is that the harmonic oscillator qualitatively gives us the right answer. But quantitatively, it gets worse and worse as energy increases, because the actual molecular potential has behavior that is not represented in the harmonic oscillator. The harmonic oscillator is perfectly drama-free the whole way up. But molecules have drama. They repel each other at short distances, and they break at long distances. And you can see that the drama starts to, I guess I'm using more drama, but you can see that things start to get worse as energy gets higher. Right, what I'm doing is I'm taking my HCl and I'm putting my energy higher and higher and higher, starting to get towards this anharmonic part, the part that doesn't look like a parabola, and my disagreements start to increase. But when I correct for those, when I make an assumption about what I think my potential looks like physically, which is that it has this asymptotic behavior that we want, my agreements are orders of magnitude better. Okay? So again, just like before, particle in a box gives us a good qualitative picture. There's nothing wrong with it. It's just that it has limits. And that we need to improve those limits, but we have a mechanism for doing that, right? All I did was just appeal to my chemical intuition. How does my potential need to look more realistic? And of course, I'm not the only person to have this thought. That's why the Morse potential exists. I wasn't the first person to think this, but how can I make the harmonic oscillator look more like a molecule? Well, you write the Morse potential, and by and large, by appealing to that intuition and then quantizing it, right, solving the Schrodinger equation with the new potential, which I don't come up, I didn't do anything more than just general chemistry ideas with that. And by doing that, and then solving the Schrodinger equation for this new potential, get new wave functions, new energies, I get great predictions. Great predictions. Right? You see this in quantum mechanics all the time, right? We come up with a simple problem, simple model for our problem, right? Harmonic oscillator, something that's really easy to solve. We can do lots of stuff with it. And then we start to think about little changes that we can make that make things more realistic. And then we revamp our model with those new changes, those corrections, and then none of the calculations we have to do change. We just change the input into our box, our Schrodinger equation box, put in new changes, and we get new energies out, new wave functions. And if those look more like experiment, that means we're doing the right thing. And that's exactly what's happened here. All right, so the question, of course, is, what do the energy levels of a Morse oscillator look like? And I think it's really interesting to think about kind of what the structure of these potentials look like. And let's go back one more time and look at our harmonic oscillator, so here's our harmonic oscillator. And what do the energy levels in this potential look like? Well, they're equally spaced. Right, here's V equals 0. It's at 1/2 h bar omega in energy. Here's V equals 1. It's at 3/2 h bar omega. There's another one at 5/2. Right? It doesn't matter. I can just keep going, but they're all equally spaced, right? I can just keep doing this. But no matter what I do, it doesn't change, right? The spacings between every level is h bar omega. Right? So if you ask the question, what's the density of states inside this potential as a function of energy? If I put my system like we did with the particle in the box in 4.2, what's the density of states of this system at any energy? Well, it's the same at every energy because all the levels are equally spaced. As long as if you think about the number of possible states per joule, well, no matter where you put your axis, your energy, you get the same density because they're equally spaced. So the density of states is constant. Right? And this goes up for infinity, right? This just keeps going. It never changes, right? Which of course we showed is unphysical. Right, so what does the equivalent picture look like for the Morse oscillator? I'm going to try to draw this as the same as I can, same as before, just to have a nice comparison. Put RE here. And remember, our potential has a sharp increase like this, and then it kind of like this. Right, this is our Morse. So this is V of R equals D sub E 1 minus E to the minus B R minus RE squared. Right, this is our Morse potential. Well, so what do the energy levels look like here? Well, the V equals 0 state, remember in our spectroscopy data, the V equals 0 to 1 transition is at roughly the same energy. Right, so that basically means that I can take, I'm going to kind of draw a correlation here. I can take V equals 0 to be roughly the same place as before. And V equals 1 is roughly at the same place too. Right, but what happened as the upper state got bigger? Right, when we get to V2 and V3, well, the gap started to get smaller and smaller. Right, the experimental frequency was smaller than the harmonic oscillator approximation. I'll just show you that really quickly. Right, V equals 0 to 1. The energy difference between them is 2886. And the QHO experiment's the same. But if you look at the 0 to 2, it's smaller in the experiment than the harmonic oscillator. The energy levels are getting closer together. And that gets worse for V equals 3. They keep getting closer and closer together. So what happens then is that these states, so the V equals 2 will no longer be directly over, but rather it's going to be slightly lower energy than it was. Right? And the V equals 3 is going to be at even lower energy than you predict from the quantum harmonic oscillator. Okay? And as you start to approach the dissociation limit, which I'll draw like this, right? This is the dissociation limit of the bond. The energy levels get smaller, more closely and closely spaced together. And then by the time you get to the dissociation limit, you just basically have a continuum of states. Right, so here, the density of states actually goes, let me think about this for a second. It goes roughly as v squared. V squared, right? The states get closer and closer together. They get more and more closer together. There's more and more states per unit energy as you get closer and closer to the dissociation limit. Right, so this idea is that this region here at the bottom which I draw with this green parabola, is very harmonic. Right, this region here is harmonic, right? Because the levels in the Morse oscillator correlate almost exactly with the ones in the equivalent harmonic oscillator. But once you get past this point, when the curve stops to look parabolic, the level spacings start to get smaller and smaller together. They no longer look harmonic anymore. I'm going to change this. I'm going to move this down to the below. And so this region right here is we call the anharmonic limit, right? The absence of harmony. Okay? And every bond looks like this. This is what the real picture of a vibrational spectrum looks like, or the vibrational energy levels of a bond, is that at V equals 0, V equals 1, right? At the bottom of the well, and of course the V at which this behavior starts to diverge from harmonic to anharmonic depends on the molecule. Right? The stronger the bond is, the sharper the potential, the more harmonic it is, right? So the agreement, of course, depends on, between Morse and the harmonic oscillator, depends on the molecule. But my point is that if we look at the low states here, V equals 0, V equals 1, right, they look very harmonic. They look like the energy, the potential there looks like a parabola, and the states there look like the ones you would have in a parabola. But as you start to go to V equals 2, V equals 3, and closer to the dissociation limit, the potential gets increasingly less harmonic. And what that causes, the energy levels start to compress. And by the time you hit the dissociation limit, you basically have a continuum of values of energy levels. There are many, many, many energy levels out there. But there's only finitely many. Because the moment you put enough energy in that you're above d sub e, it goes away. Right? You broke the bonds. Right? So there's not an infinite number of levels in here, but there's a finite number of levels in here. Right, the energy levels end. They end when the energy of the Vth level is greater than d sub e. Right, the moment that you have enough energy in the bond that you have enough to dissociate it, then you don't have a bond anymore. Right, so in the harmonic oscillator, the density of states is constant, and there are infinite bound states or bonded states. But in the Morse oscillator, the density of states increases as v squared. Or actually, let's say it decreases as energy squared, roughly. And there are finitely many bonded states or bound states. Okay. Right. So so when you do the in a couple of weeks you'll be doing the iodine lab. Iodine lab tackles vibration of iodine in a slightly different way using a slightly different spectroscopy, but the same idea is here. So that in that lab you're going to see lines corresponding to vibrational excitations in iodine, and they're going to stop at some point. And that stopping point corresponds to putting enough energy into the bond that the molecule dissociates. So you don't see any more vibrational lines anymore. You've taken a vibration and you've put so much energy into the vibration that you've dissociated the molecule. And that energy gets converted into kinetic energy of the atoms, dissociating instead of a vibration. Right? You can actually see that spectroscopically where it goes from bound to unbound. And you can use that to determine this dissociation energy. I want to show you, write down one more thing. Because this will be helpful for your iodine lab. You'll actually work with this a little bit, and also for the homework. But I just want to write a few equations down that are useful. So the energy equation for the quantum harmonic oscillator, we've written down 1,000,000 times. H bar omega v plus 1/2, right? Super easy to write down. That means they're equally spaced. Remember that v, 0, 1, blah, blah, blah. It's an integer. And what about for a Morse potential? It has a very similar form, but it's just slightly changed. I'm going to add this label W omega E. It's the same term. But there's an additional term added to it, which is proportional to V plus 1/2 squared. Okay? So this right here and this right here are the same. I need to add an H bar omega here. Sorry, I need an H bar here. H bar. All right, so you have a harmonic term, right? We call this the harmonic term, right? It's the term, it has a constant omega E, which is, again, dependent on the stiffness of the bond. Right? And it's V plus 1/2, it's linear in V. And then the Morse potential adds this new term, which adds this new constant called omega E xe, which is the anharmonic term. And it's proportional to V plus 1/2 squared. Okay, so the only thing that the Morse potential is doing in terms of energy is it's correcting the energy with a quadratic term. Right? And this number is going to be much smaller than this number. In general, so these numbers come from experiment. These two numbers come from experiment. And WE tends to be kind of on the order of 1,000 times omega E xe. Okay, so the quadratic part is about 1,000 times smaller than the linear part. So it's a small correction, right? But that's why the error only at V equals 3 for HCl is only about 4%. The term that's correcting that is very, very small. The important thing is that it's negative, right? That's what we saw. We saw that as the energy levels increase, the spacings get smaller, right? So that means there has to be a term that makes the energy smaller as V increases, and that's exactly what this is. Right, what we've done very, very simply by going from the harmonic oscillator to the quadratic to the Morse oscillator, again, we've gone to a more complicated function, but in terms of the energy for the harmonic oscillator went from a linear function in V, in an integer number, to a quadratic one. We just made one additional improvement to our energy. Right, so what the Morse oscillator actually is just a sequential improvement to the harmonic oscillator. It looks more complicated, the potential looks more complicated, but when we break it down to energies, all it does is it ultimately just adds a quadratic correction. Right? Just a small additional correction. All right? And in the iodine lab, we'll be actually using this equation to fit energies and frequencies and stuff for iodine. And we'll be able to actually, now we'll talk more about this next class. We'll actually be able to use these terms. What we'll see next class is that these terms tell you something about the dissociation energy and the potential. If your potential is very, very anharmonic, which means it's weak and floppy, omega E xe is going to be a really, really big term. So if we can measure omega E xe and we know omega E, it turns out that the ratio of these terms will tell you something about the stiffness of the bond and how strong it is. Okay, so we'll look at that next class. So what we have here, so we have this Morse potential. I'll just close up things. right? It's a physical representation of a bond. It's a slight improvement to our harmonic oscillator that gives us the right answers. And what we'll do is we'll start to think about what kind of information about our molecule can we learn using this. Okay? And that's what we'll tackle next class. All right, you guys have a good one.